talk of the afternoon. So this is two people will speak in it jointly. It's a joint talk by Anthony Joseph and Yasmin Fittouhi, starting with Professor Joseph. Over to you.
My relation with India is a little confused. I was born in India in a very big city, which I now cannot find on the map, and whose name Her Majesty's government very politely told me I could not put on my British passport. So now I am very pleased to be able to go through a portal to another very big city in India, which I had never heard of, until I discovered its name was really Bangalore, favored by the Raj and by Rudyard Kipling. With my co-author, Yasmin, we are giving a joint lecture, with me giving a sort of trailer to the main story and Yasmin doing all the diagrams and the pictures. So let me start with Richardson's theorem, or at least its consequence. So let G be a simple algebraic group, P a parabolic subgroup, and M the nil radical of its Lie algebra P. A theorem of Richardson implies that the invariant ring under the action of the derived group is polynomial, and the generators can be specified as being both irreducible polynomials and weight vectors. And of course, the first thing you ask is, what are these polynomials? So let me go to another topic, which I call orbital varieties. So let B be a Borel subgroup of G, and N the nil radical of its Lie algebra. A coadjoint G orbit, O, is called nilpotent if O intersection N is not empty. And then the components of O intersection N are called orbital varieties. Each component is Lagrangian, and indeed of the form B applied to N intersection Wn. Now here you may notice that N intersection Wn is a subalgebra of N, and it's also complemented by a subalgebra of N. So that's what makes the orbital variety Lagrangian. And here W is an element of the Weyl group. So one of the questions you can ask, which we won't deal with in this lecture, is can you quantize this orbital variety? So now let's take a very special case of an orbital variety, which I call a hypersurface orbital variety. A hypersurface in M, which is P stable, is automatically an orbital variety, and we call it a hypersurface orbital variety. Then it's rather easy to see that the generators of this invariant algebra exactly correspond to hypersurface orbital varieties. So then you might say, well, that's the end of the story. But unfortunately, hypersurface orbital varieties, or in fact orbital varieties in general, are not very easy to understand. In type A, things are simpler. Ben Lolo and Sanderson made the first progress, and following their work, myself and Melnikov classified the invariant generators and showed that there was a simple highest weight module whose associated variety was a hypersurface orbital variety. That's the end of representation theory for this talk. This work was shortly generalized for all G classical in a really amazing tour de force by Elena Perelman. So now let me go to the main subject of this talk, which is a Weierstrass section. So a Weierstrass section is a linear subvariety, E plus V, where E is a point and V is a vector space of M, in this case M, such that restriction gives an isomorphism of the invariant ring onto the regular functions of E plus V. Of course, the latter is a polynomial algebra, so a necessary condition, but it's not actually sufficient, is that the invariant algebra be polynomial. Geometrically, it means that most p prime orbits meet E plus V at exactly one point, exactly once. This means that you can give a canonical form to any orbit which meets E plus V. So you might like to ask which orbits meet E plus V. Sometimes that's just the regular orbits. And in the case of SL3 acting on its 10-dimensional representation, this canonical form coincides with Weierstrass canonical form. Now let me describe the nilfibre, which will play an important role, and adapted pairs. The nilfibre, by definition, in this case, is a zero set of the augmentation ideal of the invariant algebra. So it's where every invariant polynomial of positive degree vanishes. In general, the nilfibre is not irreducible, although it was in Costant's case, and not known to be equidimensional. So roughly speaking, you should have a Weierstrass section for each component of the nilfibre. And how to construct them? Well, the method used by Costant and by Winberg and Popov, and later by myself, was to write down an adapted pair. What is that? It's a pair E and H, with E and M in this case, and H a semi-simple element of P prime. You can think of it as being in the Cartan, such that E is an eigenvector of eigenvalue, which I should just choose to be -1. This last condition forces E to be in the nilfibre. And then you require an additional condition, namely that P dot E is dense in a component of N. In fact, sometimes you just require this for P prime, but here I require it for the whole of P. So what can you do with an adapted pair? You can choose a vector space V in M, which is a complement to P prime dot E. This last condition, I should say P dot E, I'm sorry in this case. This last condition forces the injectivity of the map. Surjectivity is much more complicated, but you have to make some estimate of the degrees of the invariant generators and the eigenvalues of H on M, and be able to relate them in this way. In the adjoint case, this relation is automatic, so we haven't too much work to do. Now we want to consider our special case, which is a Weierstrass section of E plus V inside M, where P is the group, the parabolic, acting on its nil radical M. In this case, we can't find adapted pairs. Well, sometimes you can, but not enough of them. So we have to have another method, and then we will reduce ourselves to combinatorics, messy combinatorics. In type A. In general type, we haven't yet tried. So what's the starting point? So the starting point of this combinatorics is the diagram D, defined to have columns of heights matching the block sizes of the Levy factor. Then we form a tableau with entries from 1 to n, which increase down the rows and along the columns. So that's our basic object, this tableau with entries from 1 to n, increasing in the standard sort of way. Now we think about a result of Ringel and his collaborators, who said we should join adjacent boxes in T by horizontal lines. Rather strange thing to do, but whatever, that's what he did. And you see each horizontal line goes from a box with a label I to a box with a label J. Remember, we've labeled the boxes so they have labels, and now we draw a line, so we join I by J, and that defines a root vector Xij, and it's a important but relatively easy fact that Xij is in the nil radical. That's because the way we've labeled M, and in fact this is true not only for horizontal lines, but all lines which go from left to right, from one column to another column, a different column. So what did Ringel and company tell us? This was already 18 years ago, that the sum of these root vectors generates a dense p orbit in M. This gave a complicated combinatorial proof of Richardson's theorem in type A, but nevertheless caused some excitement and was soon generalized even to biparabolics, except for some mysterious reason it breaks down in type E8. So now we want to modify Ringel, because we don't just want one regular element E tilde, we want an element E which is regular in the inner component, and we want a vector space V. So to do this, I will tell you something about the invariance. So call two columns of height S neighboring if there are no columns of height S between them. The number of generators of this invariant ring turns out to be just the number of neighboring columns. So we know that every pair of neighboring columns has to be associated with an element of V, and this is how we get that element of V. For any pair of neighboring columns of height S, place a star on the line in the S row meeting the right-hand column, and one on the remaining lines. Now, I didn't draw a picture because my colleague, Yasmin, will draw you plenty of pictures. But just imagine we have a set of horizontal lines, one on all of them, except on the S row between two neighboring columns of height S, with a star meeting the right-hand member of this neighboring pair. Now what we do is we define E to be the sum of the root vectors with 1, and V to be the sum of the root subspaces with star. And the lemma, which is relatively easy given Ringel, that the restriction map is injective and surjective at the level of fractions. Now, I don't think I have to tell you that to go from surjective at the level of fractions to surjective at the level of rings could be quite tricky. And now I can state our main results, very briefly summarize our main results in my last slide. So surjectivity at the algebra level is obtained by modifying Ringel et al. By changing the lines, and the lines have to be changed in quite a complicated way, and that's where Yasmin will come into the picture. In these new lines, you will also have ones on some of the lines, and that will define E. E will again be in the nil fiber, and you'll have stars on other lines, which will be defining V. Now, you can ask some extra questions. What about the component of N in which E sits? This we will describe as a B saturation set. That is to say, of the form B applied to a subalgebra of U. And this is rather like an orbital variety, except that U may not be complemented by a subalgebra of N. And so this component can fail to be Lagrangian. And it can also fail to generate a dense p orbit. So those are our main results. Questions are obviously, can you describe the other components in this way? And will they or will they not? When will they fail to contain a dense p orbit? Well, I must say, when I started this work, I found that it came up with so many unexpected things that I can't help but quote Oberon's in Shakespeare's Midsummer Night's Dream. This falls out much better than I could devise. Oberon had just punished his wife by sprinkling her eyes with a love potion while she was asleep, and was happy to learn from his servant Puck that she awoke and straightway loved an ass. This is the end of the trailer.
Okay. Thank you. Now
So I will leave screen if I can.
by switching, is there any questions anyone has at this point? Feel free to ask. Well, Yasmin is loading her slides.
Okay, leave screen. Did I leave it? No, I don't know if I left.
I stopped your sharing. Yeah.
Okay, very good. That's great. So I'll stop my microphone too. Okay.
Venkatesh, is
This is
over to you, Yasmin.
Yeah.
Okay. Okay, so you had a really nice introduction, and you have everything theoretical part in the first part that Tony gave. And now we are going to go in details, and I will embody them with 2 examples. Nevertheless, I will remind you some things, like, for example, some notation. So P is a parabolic subgroup of simple Lie group SNN, and that P prime is derived group, and M it's nil radical of its Lie algebra. So the invariant algebra of regular function on M by the action of P prime is polynomial, and Weierstrass section for the action of P prime on M is a linear subvariety E plus V of M, where E is just a point and V is a vector space, such that the restriction map phi that go from regular function on M invariant by the action of P prime to regular function of E plus V, and this restriction should be an isomorphism. Okay, so in certain way, V, because it's the vector space, is getting all our attention. Let's go. So how to construct Weierstrass section for derived parabolic in SNN acting on its nil radical algebra. So the conventional wisdom was to look for adaptative pair and then construct E and V. And you can use the method of constant, but it does not work all the time as said before. So what we did, in contrast, we took our detailed understanding of generator of the invariant algebra, and we construct E plus V. So therefore, I will tell you what are our generator. So I took a matrix, square matrix n by n, and I took all the entry xij, which is a standard matrix unit. So Ben Lolo and Sanderson said that the generator of the invariant of regular function on M by the action of P prime is the leading term of a minor located between 2 boxes, 2 blocks of the same size on the lower left corner of the matrix M. And they took that minor and they restricted to M plus identity. So this M plus identity is like the magic, where the magic happens. But I can't spend too much time to explain it to you. Okay, now we have minor. I want to describe it differently. And that what I will use diagram. So I take P, a parabolic subalgebra of S and N associated to P, and I will describe it as diagram D, consisting of a collection of columns whose height are the size of the block of the levy. Okay, so as you saw in the theorem of Bangalore and Sanderson, I took blocks of the same height, so I will give them a name in diagram. I said that two columns in diagram D are called neighboring of height S, if they are of height S, and are no column of height S in between. So I said even earlier that the number of generator of the invariant algebra of regular function on M by the action of P prime is equal to the number of neighboring columns. Okay, now I want to give a little bit more structure to this diagram. So what I'm going to do, I'm going to number the boxes of D from 1 to N, in increasing from top to bottom and from left to right. And the resulting is, we called Tableau. The resulting scheme is called Tableau. So here an example. So I take the example 2112. This is the levy. So I draw like this my diagram. Let's look what are my neighboring columns. So I have two couple of neighboring column. One is a neighboring column of height 2 is in blue, and a neighboring column of height 1 is in red. Now I will number them. So you see, in few minutes, I will draw lines between boxes, and I do not want to encumbersome my figures. So I will take off the boxes, but I will keep the terminology boxes. So what I mean by line between boxes, so when you draw a line between boxes of different columns, and these boxes are carrying E and G, it defines a coordinate, it represents a coordinate xij. There is an easy lemma, but not obvious, that the vector xij coming from a link is an element of M. And I can even say that every element of the basis of M is rising in this way. So the key point here is like the shape of my tableau. Okay, so if I wanted to draw lines, the obvious way, I will just draw horizontal lines. And these horizontal lines, how would you read it? I would read all this diagram as an element of M, which is the sum of the represented of each line, means x13 plus x34 plus x45 plus x26. And this is have some interesting propriety, and it was given by Ringel and his co-author. And what they say, take a parabolic, we describe it with a tableau, and draw all horizontal line between any adjacent boxes. This is what we did. And the represented element E would be in M, and that the P orbit of E closure is equal to M. Oh, really nice. So this is the element, this element E is called Richardson, but also if you saw our map phi, we wanted to prove that it's isomorphic. So in a way to prove that it is surjective, I want to prove that the P orbit of on P, the closure of P orbit on small e plus the vector space V is equal to M.
Sorry, may I ask a question?
Yes.
Could you please repeat the definition of E?
This big E?
Yes, big E, how to define it?
Oh yes, okay, so if you draw all horizontal lines, yes, and each line is represented by a coordinate. So if its a line is between E and G, so it's represent Xij. And E is the sum of all the representative of the horizontal line.
Thank you.
Okay. So yes, therefore I need to distinguish E and V in this diagram. And in order to distinguish them, I will label them. So I will label one lines by one to indicate the coordinate composing the vector composing E. and I will label star to specify the coordinate of the basis of the vector space V. So also between any neighboring columns of height S, I will label the last line, in the last row S, the right going line of the column by star. So here what we have dimension of V is equal to number of neighboring column. This is what I just said. And the number of generator of regular function on M by the action of P prime. So I want to say something. What I have in ideal, I will have each generator will have one element of V, and I would prefer to be the basis of V. This is one. And the second thing, I want to do it for all neighboring columns, means I will do it simultaneously. Okay. So I will take my previous example and I will do a labeling as a trivial labeling. What I will write, I have 3, 4 as neighboring columns. So I will draw a line, I put star. And between these two neighboring columns, 1, 2, and 5, 6, the last line is 2, 6. So I will label it by star and the rest by 1. Let's see what their matrix, where they look like in my matrix. So I have each 1 and star in different columns. And I could say that I have, you can see that if I see, okay, if I see in the big matrix, I have an invariant X43, and this X43 will be represented by this blue star, while the big minor will be equal to all these big elements. So it will be equal to X13, X26, X34, X45. So as if I'm having this big minor has 2 elements of V. It's associated to 2 elements of V. But as I said, what I want, I have one element of V, 1 element of the basis of V I associated to 1 generator. So this is causing me some problem. So what I'm going to do, since I can't move, since X43 is associated to this star, I can't really change it. I do not have leverage of moving. So I can only change this element X26. So I'll go back to my diagram. I'll just get rid of the line 2, 6, and I will look for a way to go from the first column to the 4th column. And an easy way is to have a line between 2, 4, and 3, 6. Okay. So this is a solution of Weierstrass section, but let me show you in my matrix. So you can see all the ones and are in different line and different columns. Nevertheless, my stars are in the same line, but different column. Nevertheless, if you compute this minor, you will have you have product of all the ones and only 1 product of star, which means I resolved the previous problem. So let's go back to this diagram because there is a lot of things to say. So first of all, I call composite line a line of constituted of lines labels, like where they do not share, they pass over all columns and they do over all boxes and they do not share a box. For example, here my composite line is 1, 3, 6, and the second composite line is 2, 4, 5. These composite lines are really, really nice because each time one of you draw a composite line, if they make a product of all this composite line, they will get a monomial of your invariant. Like for example, when we had this composite line 1, 3, 4, 5, and 2, 6. If you do the product of all of them, it will be also a monomial of our invariant. Nevertheless, it's not a Weierstrass section. Does not bring us Weierstrass section. This is really crucial. Doesn't mean each time you have composite line, you have a Weierstrass section. No, no, no. You need to have a specific one such that, for example, the stars are, in this case, the stars are on the same line, means no stars will affect the other one. And another way also to see it, that each time, if you want to do it in general, if each time you have two lines labeled star horizontally and one encased in the other, you know that you need to break one in order to put the other star in the same row in the matrix. Okay. So in general, I will let you deduce what are the rules that I'm following to describe this algorithm. And since we don't have luxury of time, let's do another example and see if you get the main idea. So this example is SLN 19, and the sequence that the Levy that I will use is defined by 3, 2, 1, 1, 2, 3, 2, 3, 2. Okay. So first, if you had to do it alone, you will first draw the tableau. Secondly, you will draw only horizontal line, means the regal solution. And then you will do the naive labeling. As I said earlier, if you have two lines horizontal in case one in the other, it's causing us problem. So we need to take COF 5, 9. Same for these two neighboring column, 1, 2, 3, and 10, 11, 12 with 4, 5, 8, 9. They are in case ones inside the other, and I have two parallel lines labeled star. So I need to get rid of 3, 12. And here I have 11, 14, 12, 17, and they are in case one inside the other. So I need to get rid of 12, 17. And for 16, 19, he's alone, he's good, so we'll not touch it. So let's take them off. As I said earlier, my main point is like having stars that do not, when I implement star, I do not want them to disturb the previous star. I do not want to have them to be times by them. So here I will have 6, 9, 7, 5. This is how we resolve the problem. And 6, 9 will have the label star. Similarly, for 3 and 12, I will link 6 with 12. Therefore, I will have in one row, 2 lines label star, and 3, 9, I will label it by 1. Lastly, same here, I will take 11, 17, label star, 14, 12, label 1. And this is a Weierstrass section. Hopefully by now, everybody, each time they have a parabolic, they could express a Weierstrass section simultaneously for all neighboring columns in any case. So now I want to talk about irreducible component of N. So if I'm talking about irreducible component of the nilfibre, means the nilfibre, it's not irreducible, which is really, because it's a 0 of irreducible and everybody expected it to be irreducible, which is not the case. So how to express this component? What I will do, we will construct an algebra that we call U. And this algebra is the intersection of N inter WEN, where WE is a well element that is related and chosen through neighboring columns. When you saw this N inter WEN, if you remember earlier, this is a way to relate well element with orbital variety. So what we want at the end is like our component to be an orbital variety. So Let me show you how a result that I will not prove it, but I will show it to you in our example, how things work, so that the closure of the B saturation, where B is the parabolic group of U, is a component of N, and it's contained E, and E is our E that we define for the Weierstrass section. Okay, so here how I'm going to define W. So I see that I have two neighboring columns. The first one is 1, 2, 5, 6. And what I do, I took the last box of the right column of the neighboring column, and I will move it under 2, as near as possible to 2. And since I do not have obstacles, I'll just put it under 2. And between these 3, 4, I will take the fourth box and I move it under 3. I have no obstacle, so that's perfect. The thing is, like, here it's look like an artificial, does not look really clear why, but I will explain it in a few. When I will draw the matrix, you will understand it. So here how our diagram come, and I will read them from bottom to top and from left to right to have the wordly expression of my well element, and it will be 2, 6, 2, 6, 2, 1, 3, 4, 5, and here is the same 2, 1, 4, 3, 6, 5. Okay, let me draw the matrix, the U in the matrix, and I will explain you everything. So you put it in yellow. And in the red, the encircled in red are the elements that are not touched by you. So did you remember that I told you that I moved the last box for 2 reasons? First reason is you can see that all my encircle have a star. This is a reason of it. And the second reason is to make sure that all the last column is not touched by you, or partially last column between 2 neighboring columns is not touched by you. Here is all the column. Second remark, you can see that all the component composing E is in U. Oh, okay. So I want to check it also, this construction, does it work for SNN19? So here I have 6 neighboring columns, means I will have 6 well elements. I have an element coming from this 2 neighboring column. I will take 7, I put it under 6. I do not have anything okay. And I have 4, 5, and 8, 9, and I took 9 and put it under 5. And I have this 2 neighboring column, 1, 2, 3, 10, 11, 12. I took the last box and I put it under 3. And 10, 11, 12, 15, 16, 17 is another neighboring column, and I can take the last box, 17, and put it under 12. Okay, so now I have I did not take care of 2 couple of neighboring column of height 2 is 8, 9, 13, 14, and 13, 14, 18, 19. So how I'm going to take care of them. So in ideal, I will take the box 14 and I will move it under 9, but I can't because I have the box 12. And this is an obstacle, and a box cannot jump a box. But what we can do is we can take a box 12, can push the box 12 under 9, so we will have 9 and 14. Same for the other pair. I have a box 19 having an obstacle, 17 to reach 14. So what we will do, we just push 17 under 14, and 19 will be under 16. And it will give us a well element, W6. So here is our matrix. And here, everything that U is in white, and in red, everything that U does not reach. You can see here, same remark as earlier. E, all the ones are in U. And you can also see that all the stars that represented our V is in red, and also a part of the last column between two neighboring boxes. Okay, so here's the general, but it needs a little bit work to prove it, and you saw it in example. So you probably believe me now if I state that a set of coordinates composing E is in U, and V is in the complement of U. Secondly, U is a nilfibre, and why it is a nilfibre? Because you remember that the generator is the leading term of the minor, and we are taking off the last column. So therefore, it's clear that U is in the nilfibre. I'm saying that the Borel B saturation of U is irreducible, and it's irreducible because the Borel is irreducible and U is a vector space, an algebra. And lastly, there's this equality of dimension. The dimension of BU is equal to dimension of M minus dimension of V. This is really not an obvious equality, but this is what we need to have a component. This is what we expect as a dimension of the component. Now we can say that the closure of BU is a component of N containing U. Okay. So if you remember earlier when we defined U, we used N intersection W, and I told you in ideal I want it to be an orbital variety. So I'm expecting that what I want that to have is like irregular. And what I mean by irregular, E is regular if the P parabolic is dense in a component. Okay. Therefore, I would want to have dimension of E is equal to dimension of M minus dimension of V. That this, we just saw it. So the E I gave in SNN 19 was not regular. Therefore, in hope to have orbital variety, what I will do, I will add some coordinate to E to fill whatever I'm missing. So what I'm adding, I will go to add these two boxes in black. I will add them. This is not randomly chosen. It's really, there is a lot of technicality and work, and we have like a lot of issue to find them, but I do not have time to explain them. And here our diagram, how it became. So I added two ones, and I will draw them in orange. It goes 6, 11, and 11, 19. In this new diagram, there is something quite disturbing, that we have a cycle of line label ones. So we have 6 go to 11, 11 go to 19, 19 go to 17, 17 go to 6, and this is a cycle. This cycle in a way crushed a little bit our hopes, and I will explain you why. One more notation, I note big E, a vector space spanned by the representative of lines label 1. Okay, and I will show you that the component C has no dense p orbit, where we were hoping to have a component to be a p orbit. So a proof, or the idea of the proof, because there is a lot of things I will not talk about them. So suppose that we have an orbit, p orbit inside my component. So it means I have an E star in M, such that the closure of the action of P on E star is equal to the BU closure, and it's equal to P dot E closure, the action of P. So if I'm looking well here, I have P dot E star, and here I have P dot big E star. So clearly, if I have equality, at some point E star is in E, could not be in, yes, it could be in P, but it is what is given it. So therefore, E star in big E. So therefore, if E star is in E, and after some calculation, we just conclude that if I want to have this equality, I need just to prove that the closure of the Cartan action by E star is equal to E, big E. But no, it could not be equal. And this is due to the cycle. So the weight of the bases of E are not linearly dependent, are linearly dependent, are not linearly independent. Therefore, for any element of E star, we will never have that the closure of H E star equal to E. Therefore, there is no dense orbit in the component. Okay, this is really sad because, you know, if we had a dense orbit variety, if we had a dense orbit variety, it will be easy for us to construct a Weierstrass section. Since we do not have anymore this information because we found a counterexample, so we need to pass by this messy, but also kind of algorithm and computation to find a Weierstrass section. So what are the questions that we could answer, or we can't, or we will answer in near future is, when a component of N admit a dense orbit, and secondly, what are the components of N? Okay. Now I finished.
Okay, let's thank the speaker. Are there any more questions? Any further for both the speakers? I mean, any questions for both the speakers?
So can I ask a naive question? Is there an analog of Springer construction of Weyl group representations for this case? I feel like we're almost there labeling this component.
Can you repeat, please?
So the Springer construction of the Weyl group representations on the cohomology, in the top cohomology, I need exactly to label components in the ordinary Springer fibers. And now you're doing something very similar and getting very tight information on those components. Is there some analogous analog of the Springer correspondence?
So let me just say that if I'm on, can you hear me?
Yes, I can hear.
Yes, I can hear you. So you could ask, I think maybe you're asking this question, can one use the Springer correspondence to calculate the number of hypersurface orbital varieties? And this is possible in type A. But the trouble is that some of the Weyl group representations which come from the Springer correspondence don't correspond to orbital varieties. And we don't know really a good way of writing them down. And the first case that this happens is in type B2. There are two one-dimensional representations, one of them which is generated by the product of the short roots, and one generated by the product of the long roots. One of them, I forget which, corresponds to a hypersurface orbital variety, and the other one corresponds to a representation coming from Springer, which is not corresponding to a trivial representation of the component group. So we have to subtract all these, let me call them bad representations, and count all the others. And then we get the number of hypersurface orbital varieties. But we don't know how to kill these bad ones. So in type A, there aren't any. So in type A, we have a formula, which is a combinatorial formula, which we haven't worked out yet because we have to compute representations. and we can have a formula for the number of hypersurface or orbital varieties. In general, we have this knotty problem of deciding which of Springer's representations correspond to orbital varieties.
That's great. Thank you. That's very helpful. Yes.
Okay.
There are more questions?
May I ask a question?
Please.
So you started with your diagram, right? And then you fill with numbers. These numbers increase from top to bottom and from left to right. Yes. So if your diagram is the Young diagram, then these are standard Tableau, and the number basis in representation of the symmetric group, right? So I wonder if the number has any sense for a general diagram. So if your diagram is not a Young diagram, but something, so does this measure something or?
Well, there's 2 points. One is that if you do this, you get other vectors in the Specht module, which are linearly dependent on the ones you got. So that's the first thing. You do get vectors, and some Frenchman, I think, worked out the relations. The second thing is that when you do this shifting process, you get a different Weyl group element. And the point is that an orbital variety is not given by a unique Weyl group element. And what we did was something very strange. We took all these algebras and we took their intersection. And then we claim that B acting on the intersection of the algebras gives a component of the intersection of B acting on the algebras. And this is completely wild. I mean, why should this happen? Obviously, you have an inclusion, but that's all. And we believe that we were lucky in choosing the correct Weyl group elements, which were got by not collapsing the diagram, because of course you could take one of these diagrams and squash it over and get a standard Tableau. So this is something which we don't understand. It just works. And incidentally, it's quite difficult to imagine how you would calculate the dimension of a group acting on a vector space. I mean, I don't think there are any general formulae. So we believe that by luck, we got a good Weyl group element. So is that an answer? It's not an entire answer because we didn't work out what happens when we take the bad Weyl group elements, but that was. So you see, we instead of taking an intersection of the B on U's, we take an intersection of U's and apply B. We get an irreducible component of the first thing, and that's a miracle. I mean, that's just strange.
Thank you.
Okay, any more questions? If not, let's thank both of the speakers again for their joint seminar.
Thank you.
And